Hello dear students, welcome to my YouTube channel. Today's topic is theory of magnetism. So magnetism has a wide applications in industry in day-to-day life. So there are certain applications of magnetism listed below like this. We can use magnets in debit and credit cards, door opening systems, audio tapes, magnetic dart games, magnetic letter boards used in kindergarten for students, loudspeakers, magnetic separation, that is from dust. If we have to separate the iron particles, then we use this method of magnetic separation. Cabinets of cupboards, electric fan, computers, electric oven, vacuum cleaner, barcode systems, electric bell, all these use magnetism. The medical application of magnetism is in magnetic resonance imaging. We call it as MRI. Today's life is very fast, so in such fast life we use magnetism in magnetotrends, which is called as magnetic levitation stress. So let us have the theory of this magnetism. Magnetism is a word which is come from the Greek place magnesia. Magnesia, it is a place which is observed in city Greece. So where magnets are observed or magnets are formed in the form of rocks, so that place was magnesia. So from that word magnesia, magnet has come here. A magnet is a material which has a property of attracting ions. So magnet attracts iron particles towards itself. The metals such as iron, nickel, cobalt, this can be magnetized by different methods, and then they are called as artificial magnets. These artificial magnets can be in different shapes such as bar magnet, magnetic needle, horseshoe magnet, cylindrical magnets or circular magnets. The main purpose of preparing these artificial magnets is that these artificial magnets are stronger than natural magnets. So every bar magnet, it attracts iron, nickel, cobalt, steel, etc. towards it. It always rests in north-south direction when suspended freely, and hence a magnetic compass is used to find direction. So every bar magnet has two ends. We call these two ends as pole. The first pole is north pole and second one it is a south pole. So like poles always repel each other while unlike poles always attract each other. If we consider a south pole of one magnet and north pole of another magnet, if south pole of one magnet and north pole of another magnet is brought closer, then there will be attraction. But on the contrary, if two south poles or two north poles, they are brought closer, then there will be repulsion between these poles here. Or we say that there exists a force of repulsion between two like poles. There exists a force of attraction between two unlike poles. Now suppose a bar magnet is given here. If it is broken, suppose it is broken into two pieces, then two cases might occur there. This first one, that is the two poles get separated, or each piece which is broken, it has a south pole and a north pole. So which one is correct here? The first part, that is first option, that is each pole, south pole and north pole, will get separated. This is wrong one. We say that each pole, each bar magnet, it will have a south pole as well as a north pole. That is, we say that monopole does not exist. Whenever a bar magnet is broken into pieces, then each piece has a north pole and a south pole. That is, magnetic poles exist in pairs only. So a magnet can magnetize another piece of iron. The strength of magnetic field is maximum at the poles, whereas at the middle it is 0. Unit of magnetic field strength, it is given by the unit Weber. Now we will study magnetism as compared to electrostatics. What we have learnt in electrostatics, depending on that we will compare or study magnetism. In electrostatics we have considered electric charge. Now in magnetism we consider magnetic pole. So electric charge is a property which produces electric effects around it. We simply define a magnet as a material which has a property of attracting iron. Electric charge strength, it is given by symbol Q. We write symbol M for magnetic pole strength. Coulomb is the unit of electric charge strength, whereas magnetic pole strength, it has unit Weber. Two types of electric charges are there, positive and negative. In magnesium, we say that two types of poles are there, north pole and south pole. Like charges repel each other while unlike charges attract each other. Here we say that like poles repel while unlike poles attract each other. In electrostatic, we have important law which is Coulomb's inverse square law of electrostatics. It says that the force of attraction or repulsion between two electric charges is directly proportional to the product of their charge strength and inversely proportional to the square of the distance between them. Same law is here in magnetism. We call it as Coulomb's inverse square law of magnetism. So it says that the force of attraction or repulsion between two magnetic poles is directly proportional to the product of their pole strengths and inversely proportional to the square of the distance between them. That is, if pole strength increases, then force of attraction or repulsion also goes on increasing. On the contrary, if distance is increased, then force of attraction or repulsion it decreases. In electrostatics, we say that force is directly proportional to Q1, Q2 and it is inversely proportional to T square. Q1, Q2, these are the charge strengths separated by distance d. Combining both these, we write F is directly proportional to Q1, Q2 upon T square. Every time we remove this proportionality symbol and take a constant here, this constant in this case it is 1 upon 4 pi epsilon. Epsilon it is called as permittivity of the medium. Similarly, in magnetism, we consider F directly proportional to M1, M2 and F inversely proportional to T square. So M1, M2, these are the pole strengths of two poles separated by a distance d. Combining both these, we write F is directly proportional to M1, M2 upon T square. Again, we remove proportionality symbol and take a constant here, and this constant it is 1 upon 4 pi mu. Mu in this case it is called as permeability of the medium. In electrostatics, we have defined dielectric constant or relative permittivity of the medium as ratio of permittivity of the medium to permittivity of the free space or vacuum. We write it as K is equal to epsilon upon epsilon 0. K is the dielectric constant, epsilon is permittivity of the medium, epsilon 0 it is permittivity of free space. Similarly, in magnetism, we write relative permeability of the medium. So it is the ratio of permeability of the medium to permeability of free space or vacuum. We have equation mu r is equal to mu upon mu 0. Mu r it is relative permeability of the medium. Mu it is permeability of the medium and mu 0 it is permeability of free space or vacuum. Now in electrostatics, we consider electric field. So electric field it is the space or region around the given electric charge in which force of attraction or repulsion due to the charge is present. Similarly, in magnetism, every magnet it has certain space or region around itself in which force of attraction or repulsion is present. That space we call it as magnetic field. So magnetic field is nothing but the space or region around the given magnetic pole in which the magnetic force of attraction or repulsion due to the. So in electrostatics, we have seen that electric field strength it is given by a quantity called as electric field intensity denoted by symbol capital E. So it is simply the force acting on unit positive charge placed at that point. So its unit was Newton per coulomb or volt per meter. We write electric field intensity as force upon charge, or E is equal to F upon Q, that is 1 upon 4 pi epsilon 0 into Q upon K d square. Similarly, in magnetism, we consider magnetic field intensity denoted by symbol capital H, and it is the force acting on unit north pole placed at that point. So its unit is Newton per Weber. We write magnetic field intensity as force per unit pole strength, or capital H is equal to F upon M is equal to 1 upon 4 pi mu 0 into M upon mu r d square. So electric field strength is maximum near the charge and it goes on decreasing with distance away from the charge. Near the charge, distance will be less, so force will be maximum and hence electric field strength will be maximum. Away from the charge, as distance is increased, force will go on decreasing and hence electric field strength will be minimum. Similarly, in magnetism, we say that magnetic field strength is maximum near the magnet and it goes on decreasing with distance as we move away from the magnet. In electrostatics, we have considered electric lines of force. whenever a test charge is brought in the electric field of given charge, then it will be attracted or repelled by the given charge. So we say that it moves along a certain path, and that path along which this unit positive charge or test charge will move, it is simply called as electric lines of force. Similarly, in magnetism, we consider magnetic lines of force, the path along which a unit north pole will move when placed in the magnetic field. It is called as magnetic lines of force. We have certain properties of electric lines of force as well as the properties of magnetic lines of force. The first property, electric lines of force are imaginary in nature. Similarly, we say that magnetic lines of force are imaginary in nature. Electric lines of force starts from positive charge and ends at negative charge. In magnetism, we say that magnetic lines of force starts from north pole and ends at south pole, but only outside the magnet. Inside the magnet, magnetic lines of force starts from south pole and ends at north pole. And that's why we say that magnetic lines of force forms a closed continuous loop. We can show in figure here. Electric lines of force starts from positive charge and ends at negative charge. So direction of electric lines of force, it is away from positive charge, and for negative charge it is towards the given charge. In magnetism, we can show here by this figure, magnetic lines of force outside the magnet, its direction is from north to south, but inside a magnet its direction is from south to north. That's why we say that magnetic lines of force forms a closed continuous loop. A loop is formed here. We have another properties of electric lines of force and magnetic lines of force as well. Whenever we have to find direction of electric field at any point, then we draw a tangent to the electric lines of force at that point, and the direction of this tangent gives the direction of electric field at that point. Similarly, if we have to find out the direction of magnetic field at any point, then we draw a tangent to the magnetic lines of force at that point, and then the direction of this tangent, it gives the direction of magnetic field at that point. Electric lines of force never intersect each other. Similarly, magnetic lines of force never intersect each other, because at every point direction of magnetic lines of force or direction of magnetic field, it will be different, and that's why magnetic lines of force never intersect each other. Electric lines of force are parallel to each other in uniform field and curved in non-uniform field. Similarly, we say that magnetic lines of force are parallel to each other in uniform field and curved in non-uniform field. Electric lines of force can pass through insulator but cannot pass through conductor. In magnetism, we say that magnetic lines of force are not affected by non-magnetic material. Non-magnetic materials like air, paper, wood, plastic, etc. For strong electric field, electric lines of force are very close to each other, while for weak electric field, electric lines of force are less crowded. Here we say that for strong magnetic field, magnetic lines of force are very close to each other, while for weak magnetic field, magnetic lines of force are less crowded. That is, strong magnetic field means number of magnetic lines of force is more. That's why we say that they are crowded or very close to each other. But if weak magnetic field is given, then magnetic lines of force are separated from each other. That's why we say that they are less crowded. Electric lines of force, they contract longitudinally and expand laterally. Similarly, magnetic lines of force contract longitudinally and expand laterally. In electrostatics, we consider electric flux given by psi, that is total number of electric lines of force starting from a charge. We say that its unit is coulomb. Similarly, we say electric flux density, electric lines of force passing normally through unit area, and unit is coulomb per meter square. So total number of electric lines of force starting from a charge, it is electric flux, and total number of electric lines of force which crosses unit area, it is called as electric flux density. In magnetism, we say it is magnetic flux denoted by symbol phi. It is the total number of magnetic lines of force starting from a pole, so its unit is Weber. We consider magnetic flux density, which is also called as magnetic induction, denoted by symbol B, capital B. So magnetic lines of force passing normally through unit area, it is simply called as magnetic induction. and its unit is Weber per meter square, which is also called as Tesla. So total number of magnetic lines of force starting from a pole, it is magnetic flux, whereas total number of magnetic lines of force which crosses or passes through unit area, it is simply called as magnetic induction. We have a relation between D and E, that is magnetic flux density and intensity of electric field. So electric flux density is always directly proportional to electric field intensity. Similarly, we have a relation between B and H, that is magnetic flux density or magnetic induction and magnetic field intensity. The magnetic flux density is directly proportional to magnetic field intensity. That is, as magnetic field intensity goes on increasing, the magnetic flux density also goes on increasing. Thank you very much. If you like this video, you can like and subscribe to my YouTube channel. Thank you very much.